A very classic example or question that's often considered when we talk about buoyancy. So the question I have is here, I have a toy ship that's floating in a bathtub when a set of quarters are placed on the ship and the ship continues to float. So quarters, of course, are going to sink if they're actually placed in the water. This is similar to a cargo ship in the ocean that's carrying large crates and so on. We take note of the water level in the bathtub when the toy ship is actually floating with the coins on there. And the question is, what happens to the water level in the bathtub when the coins are actually placed in the water as opposed to them actually floating on the ship? Does the water level rise? Does the water level drop? Or does the water level stay the same? So in this example, I have a demonstration, or I have a simulation. I can't make a ship, so my ship is just going to be a wooden block. And just a couple of things to note, the water level starts off at 100 liters. My water density is 1 kilogram per liter, so this is fresh water, and I've set gravity to 10. So if I place the wooden block in the fluid, as expected, because it's floating, the buoyant force is exactly equal to the weight of the block. And the fluid displaced is 4. The weight of the fluid displaced should equal the buoyant force. So if I take 4 times 1 times gravity, 4 times 1 times 10 is 40, and that gives me what the buoyant force is. So I don't have coins either, but I do have a block of aluminum that's going to represent my coins. So I have 30 newtons, a 30 Newton block of aluminum. And I am going to place that block of aluminum on the wooden block, and the whole system is going to continue to float. Because the system is in equilibrium, the buoyant force, the total buoyant force, should equal the total weight of the system. And so I have a total weight of 40 newtons of the wooden block, 30 newtons of the aluminum block. Total weight is 70, and indeed the buoyant force is 70 newtons. The volume of the fluid that's displaced is 7 liters. And if I calculated the buoyant force, 7 times 1 times 10 is 70 newtons. So it all makes sense in terms of the volume of the fluid that's displaced. So the block itself here, the wooden block, is able to displace extra fluid to account for the weight of the block. So how much extra fluid is it having to displace? So let's take this off for a moment. For its own weight of 40 newtons, it has to displace 4 liters. So when I put an additional 30 newtons on there, it has to displace an additional 3 liters of fluid. So the block itself is able to displace more fluid because it's a large block, and it has enough space to displace more fluid. So the question is, what happens if I take this block, this aluminum block, and I place it in the fluid? Is this water level going to go up? Is this going to read a higher number? Or is it going to go down and read a lower number? So let's just go ahead and do it. So I put this in here, and the volume of the fluid displaced is now 5.11. So what has happened? The water level has actually gone down instead of gone up. So let's think about this in terms of what's going on. So first of all, the buoyant force has gone down, the overall buoyant force. So I have 40 newtons on the floating object. It still has to, if it's floating, the buoyant force has to equal the weight. But the object that has now sunk does not have a buoyant force equal to the object's weight. It has a buoyant force that's less than the weight of the object. So the overall buoyant force here is 40 plus 11.11, which is 51.11, which is why the volume of the fluid displaced here is 5.11. So if I calculated the total buoyant force on this whole system of both blocks, 5.11 times 1 kilogram times 10 is 51.1, which is what I get for the total buoyant force. The other thing you can think about with this is that in terms of the fluid that's displaced, if I come back up here, we know that when I place the block, the aluminum block on here, it has to displace an extra 3 liters of fluid in order to account for that buoyant force. But what is the volume of the block itself? The volume of the block itself is only 1.1. So when I place the block in the fluid, I can only displace a volume of 1.1 liters, which means that the buoyant force on the block here can only have a maximum value when it's in the water of 11.11. So if you have an object that is floating and you place something on it that's more dense than the fluid, as long as it has a large enough volume, like this wooden block has a large enough volume that it can displace enough extra fluid to hold up that weight that's on there, then once you take that object off and you place it in the fluid, the water level is always going to go down. So hopefully that makes a little bit more sense in terms of what's going on. So of course, what happens? The water level drops. If we consider the same toy ship, but this time we put a set of wooden blocks on the ship, and the wooden blocks have the same weight as the quarters. So in this case, I'm going to put a wooden block on there that has the same weight as the aluminum block, and of course wood floats. We could take note of what the water level is in the tub when the toy ship is floating with the wood block, and we want to know what happens if I take that wood block off of the toy ship and I place it in the water. Does the water level rise? Does it drop, or does it stay the same? So let's examine that case. So I'm going to change this to a wooden block, and I am going to change its mass to 3 so that it has the same mass as the aluminum did. Now, one thing you should notice is of course, it has a different density. So now it has a larger volume because wood is less dense than aluminum. So in order to have the same weight, I have to have a larger volume. So I'm going to place my wooden block on top of my ship, my toy ship, which is my larger block here. And I note that because the total weight of the system is still the same, 30 and 40, the total buoyant force is still 30 newtons. And so the water displaced here in my container is 7 liters, which accounts for the 4 liters needed for the first one and the additional 3 liters needed for the second weight of 30 newtons. So now I'm going to take off, so the question is, here's my water level. What's going to happen to the water level when I take off the wooden block and I place it in this water? Is the water level going to rise? Is it going to drop, or is it going to stay the same? So I place it in there, and the water level stays exactly the same. And the reason it stays the same is because both of the objects are still floating. So if I look at the total amount of buoyant force here, I need 40 newtons of buoyant force for the first block. I need 30 newtons of buoyant force for the second block. I add those together, that's 70. They're both floating, and I have 7 liters. So the volume of the fluid displaced is the same, and the water level is going to be exactly the same. It's just that when I place the block on top here, that block, the bottom block, is able to displace an additional 3 liters of fluid to account for the weight that was on top. And when I take it off, the other block is able to displace that same amount of fluid. And so the total amount of buoyant force is the same.